to the point where it doesn't settle out of the atmosphere very quickly at all. And so we've got different size fractions of particles that we worry about. Basically, the more that we learn about smaller particles, the more that we worry about the size or the health impacts of smaller particles. And so we used to worry about PM10, which is particles that have a diameter smaller than 10 microns. And then we learned some more about the health impacts of PM2.5, and now we have a PM2.5 standard. And then the future might be smaller yet, might be PM1, might be PM0.1, and that's the type of health effects research that's going on right now. There's lots of different things that can be present in those particles, depending on the source from which they originate, whether it's windblown dust or a diesel engine. You get a very different composition and nature of particle that is floating around in the atmosphere. So health effects of particles, this is data from one of the earliest acknowledged health effects event, the so-called famous London fog event. And this happened in London, England in December 1952, and a severe winter stagnation event occurred where the atmosphere just got very, very quiet, and all the things that were burning in London at that time stayed very close to the ground because the atmosphere was so stagnant. And so these pictures on the left here are not nighttime pictures. These are actually pictures at noon in London during this fog event, where they had to drive the buses around with the headlights on, and they actually had to have somebody out in front of the bus to make sure the bus didn't hit somebody that they couldn't see more than 10 or so feet in front of their face. And so we don't experience these types of concentrations anymore in the United States, but they were they illustrated some of the health effects very clearly. And so on the right side here is a plot of the date in December 1952, and on the vertical axis is the number of deaths per day, and then also the concentration of the different pollutants. And so deaths is the square here, and sulfur dioxide and smoke, which is what particles were, that's smoke particles, are plotted here. And you don't have to be a real statistician to see that there's a real cause and effect relationship there. And so as a result of this, the folks in London banned the burning of coal for heat because they were worried about this being a source of particle air pollution and causing excess deaths. Well, it turns out that you don't have to have those really severe PM events, particle events, in order to cause a health effect, but you do need to be better at statistics in order to observe it. And so this is data that is taken from a very famous study now, the so-called Harvard Six City Study. And this was a study of air pollution and mortality in 6 cities in the United States. And they were looking at the long-term effects of particle air pollution, accounting for all the other lifestyle things. Did the person smoke? What was their diet? How much exercise did they get? They tried to take all those other confounding factors out of the analysis and just looked at the effect of air pollution, both sulfate particles and then just total fine particles. And what they observed was that there's a very strong correlation between the fine particle concentration on the lower axis here and the excess rate ratio of death, mortality, on the vertical axis. You get this nice linear relationship where the higher the particle concentrations are, the more people die, is the take-home message from that plot. This is the reason that we have a PM2.5 standard today. Basically, this evidence from epidemiology saying that there is a relationship between particles and mortality. And of course, a lot of people were very concerned that decisions were being made with not enough information. And so this study has been scrutinized. And other studies have been done with the same format. This has withstood the test of time. There is a relationship between particles and excess mortality. And this characterizes it one of the first pieces of evidence for PM2.5 health effects. So where are ozone and PM2.5 problematic pollutants in the United States? This is a plot of the concentrations of ozone in the United States, and the different colors of the circles here, each circle represents a monitor that is maintained and collected in the Air Now Observation Network. Lots of different agencies run these monitors, and EPA sort of coordinates the data and presents it in this format. The color of the circles represent the concentration range of ozone, and red being the highest concentrations from 105 parts per billion up to 125 parts per billion. And you can see, California and Houston are sort of moved back and forth for who's got the ozone title every year. And so you're seeing here those two places light up, but it's clearly the case that California has an ozone problem that is persistent. We've been trying to solve this since the 1960s, and we've made a lot of progress. If you would have drawn this diagram 20 or 30 years ago, you would see much, much higher concentrations. And so progress has been made, but we've also got better at understanding the health effects of these pollutants, and we've still got more work to do. And California is one of the places with the most severe ozone problem. This is a similar picture for the spatial distribution of pollutants. Now I'm looking at particles, PM2.5, and this is showing the annual average concentration because we think that annual average concentrations are the best indicator of possible health effects. And so again, the format of the plot is the same, where we're looking at which areas have the highest concentrations, and the red dots would correspond to that. And of the 6 red dots that you can see on this page, 4 of them are in California, Los Angeles here, and then Central California, moving up to where we are sitting around the Sacramento area. And so it's clear that California has some of the most severe, if not the most severe, ozone and PM2.5 problems across the whole United States. So obviously, that's a big deal. And this is one estimate of the potential consequences of that air pollution. And so we're looking at the health impacts of air pollution in California per year, estimated by the California Air Resources Board. And by that estimate, and there's uncertainty associated with these numbers, but it gives you an idea of the magnitude of the problem. Around 7,000 people a year die that would not have otherwise died because of air quality problems in California. 9,000 hospitalizations, 1.7 million incidences of respiratory illness, school absences and lost work days. And so I'm not going to try to put a value on human life, but this is obviously a very, very serious problem that California has to tackle in trying to solve this air pollution problem. We've made a lot of progress over the last 30, 40 years, and there's a lot of people working very hard to continue making progress. And so it's clear that we're going to get there. But the question is, what penalty will climate change impose on us? And that's what I'll try to address today. So why does California have that severe air quality problem? Well, it turns out that California has one of the 10 largest economies in the world. I'm Canadian, and I often make this joke, but if California declared itself its own country, it would push Canada out of the G7. That's how big its economy is. But you've got that economy operating in a very confined set of air basins. So this is just a topography view of California, and we're, again, I wish I had a laser pointer, but I don't, so I'm making the mouse work. We're up here in Sacramento. This is the lower part of the San Joaquin Valley, and then Los Angeles, tucked here in the South Coast Air Basin. All that economic activity happens in these very, very confined air basins. And so California is very environmentally progressive, and we've been trying really hard to control our emissions, but the economic activity is so high, and it's happening in these confined air basins that trap the pollutants close to the ground. We have lots of sunshine here. That's why we have such severe air quality problems. And so it's not that we're sloppy or lazy. There's a lot going on in the state, and the topography sets us up to be susceptible for air pollution problems. So we're spending a lot of money and a lot of effort trying to control it. It's a natural question to ask, is climate change going to help us or hurt us, or make some things better, make some things worse? What's going to happen to air quality in the presence of climate change? And it's a very natural thing to ask because half the air quality problem is related to weather. And climate is just the long-term trend of weather. And so it matters how hot it is for air quality problems. It matters how deep is the inversion depth. And I'll talk a little bit about what the inversion depth is for those of you who aren't familiar. We have to think about how these things are going to shift in the presence of climate change. So we know that temperatures are going to get warmer. I pulled this slide from the IPCC fourth assessment. You've probably already seen it in some of the other talks that have been presented in this series. But just looking at historical trends for temperature over North America, have an increase in temperature that can't be explained using models that have only natural forcing. We know that anthropogenic activities are affecting climate, and then projections of what's going to happen in the future are a significant increase in temperature. Also increases, though, in maybe the water content of the atmosphere. What's the humidity going to do? Changes in precipitation. changes in the structure of the atmosphere, how much mixing there is. There's lots of different things that are going to happen simultaneously, and we've got to think about all of those things if we're worried about air quality. One of the tools that we use to try to examine this is a mathematical description of how all of that stuff works together. And so we try to represent each one of the boxes that's in this plot with a set of mathematical equations that describe the chemical reactions that happen in the atmosphere, or the condensation and evaporation. We have some knowledge of the inputs to the system, the emissions inventories for both gases and particles. We describe how those things will move around in the atmosphere and maybe deposit to the earth, all in the presence of this wonderful sunshine that we have in California. And so that air quality model is the type of thing that we're going to use as one of the tools to try to understand how climate change will influence the system, because theoretically all of the physics that describes how temperature affects the pollution is already in this model. All we should have to do is change temperature, and we should be able to observe how the pollution will respond. So one of the subtleties then is how we track the particles in this model, and I won't go into a lot of detail with that today because I don't think I have time. I'm supposed to leave time for questions at the end, so I'll make sure I try to get to the end. So, but just some flavor of the types of things that we do. When we put a particle into our simulated atmosphere, we worry about how that particle moves around, but we also worry about how that particle will either have gases condense onto it and convert from a gas to a particle, and that actually turns out to be a big part of the PM 2.5 number in California, is that secondary pollution that forms. And so we have very detailed models that are trying to predict that for both the salts that are out there, the sulfates, the nitrates, the ammonium ion, the inorganic salts, as well as the secondary organics. And this is just a quick snapshot of what we're doing in the particular study that I'm going to talk about today. And then we have a lot of complexity in terms of particles from different sources, and this will mean something to the folks that do this, and maybe not so much for the folks that don't do this for a living. But basically, in each grid cell, this is how we would represent the particles. Each particle size is emitted from the source. It has different chemical composition, and it interacts with the atmosphere differently. The different colors here represent different components, the nitrates, the sulfates, elemental carbon, organic carbon. And then we also happen to know where these particles came from when they were released to the atmosphere, and so we can use this as a source apportionment tool. But again, that is not an important feature of what I'm talking about today, so I won't focus on it. So the modeling domains that I'll look at two modeling domains, one for Central California, and this is the lower part of the San Joaquin Valley, and then one for the South Coast Air Basin, where Los Angeles is. About 15 million people here, about 3 million people here, but it's growing rapidly. This is the part of California that's growing most quickly because of the cost of housing. And so you have to worry about both air basins if you think about climate change 40 or 50 years from now, what's going to happen. There's going to be a lot more people in Central California than there is right now. I'm going to look at historical episodes. And the first part of what I'm going to talk about is just looking at historical episodes and saying, what if the temperature would have been warmer? What if this would have happened? What if that would have happened? The reason that we do that is because atmospheric chemistry is nonlinear. And so you have to have the right starting point in order to say what's going to happen in response to a perturbation. It doesn't do you any good to do the perturbation unless you know for a fact you're at the right starting location, because of the nonlinearity, you might get the wrong answer. And so the episodes that I'm going to look at are old episodes because it takes a long time to apply a model to one of these episodes and to validate it and get some confidence in it. And so the episodes that I'm going to focus on are things that we've done a lot of studies with. We're very, very confident that we know what we're talking about. We know how the air pollution works in those episodes. And so that's why I'm going to use those as the starting point. So the first one is back in 1993. It was a really, really hot episode for Southern California, 35 degrees Celsius inland. All of the episodes have an elevated temperature inversion that basically puts a top on the box. And so all the emissions get trapped in this box with the mountains or the sides. And the top of the box is the temperature inversion, which prevents mixing from going, carrying the pollution away from the surface. And then the surface winds were light onshore. This is a plot of the spatial distribution of the predicted 1 hour average ozone concentrations on that day, September 9th, 1993. So we've got the coast of Los Angeles here. We've got our offshore islands, Catalina, central Los Angeles here. and we predicted this buildup of this severe ridge of ozone concentrations, almost 300 parts per billion. Just for reference, a health-based standard, one health-based standard that you can look at is the 1 hour ozone concentration, and you would not really want to breathe more than around 90 parts per billion of ozone continuously. And so we were almost 3 times the standard, more than 3 times the standard for this particular episode. And we have some confidence in our model because we compare our model to actual measurements during that episode. And so this is a plot. Every panel of this diagram represents ozone concentrations at an individual site, and the sites are labeled in the upper right corner. The lower part of the plot shows the time of day, and the vertical axis in the plot shows the ozone concentration. I will pay somebody $10 if you give me a laser pointer. This thing is driving me nuts. So the lower part of the plot is the time of day. The vertical part of the plot is the ozone concentration. There's 3 lines in the plot. One of them is the observation. One of them is the prediction using one chemical mechanism in the model, and the other one is a prediction using a newer chemical mechanism. What I'm trying to show with this plot is that all 3 lines are very, very close together, and so we are pretty sure that we understand the ozone dynamics during this episode. The lines aren't perfect, and I would have cheated. Oh, this will work. I'm old school now. This is great. You would think I cheated if the lines were right on top of each other, because no model is perfect. You can't capture everything that's happening in the atmosphere. It's a chaotic, turbulent place. But what I'm trying to convey with this plot is that we're getting the major features of the ozone chemistry right. And so that means that we would have some confidence in our predictions about how ozone chemistry would change in response to different environmental variables. This is a plot of the increase or decrease in ozone concentration as a function of location that would result if the temperature would have been 5 degrees warmer on that day. And so the base case concentrations were 300 parts per billion. This is how much extra ozone you would have gotten if you would have had a warmer temperature. And it's around 40 parts per billion, so almost 10% ozone at the location where the peak ozone occurred. So this has been observed in a number of different studies using a couple of different techniques, and I'll talk about another way to get at this question at the end of my presentation. But basically, hotter temperatures speed up the gas phase chemistry. They encourage the emissions of more volatile organic carbon compounds, and they enhance ozone production. And so in almost all areas, you see an increase, and in the area that had the original peak, you're seeing an increase of almost 10% additional ozone concentrations in this particular episode. But temperature is only one variable that we can perturb. We can also perturb the amount of water vapor that's going to be in the atmosphere. And the last slide assumed that the absolute humidity stayed the same, which means that if you make the atmosphere hotter, the relative humidity actually went down because hotter atmospheres can hold more water. If we would have made the other limiting assumption, which is that the relative humidity stayed the same, and the temperature went up by 5 degrees Kelvin. This is the additional ozone that we would predict at 3 o'clock in the afternoon. And instead of 40 parts per billion of additional ozone, you're seeing 67 parts per billion of additional ozone. And that makes sense because in California, at least, in our air basins, water vapor acts as a source of hydroxyl radical, one more oxidant to chew up and get the chemistry rolling. And so it encourages even more ozone formation in the presence of that additional water vapor. The next variable that we chose to look at was mixing depth. And again, mixing depth is the height of the box. The mountains form the sides of the box. When the temperature inversion forms, you have a certain depth of the atmosphere that the emissions can mix into, and then they stay trapped there. What would happen if the mixing depth had increased by 50%? And this is the ozone picture. We're seeing something interesting here where some concentrations in some regions are going down while others are going up. And this is where you get back to the nonlinear nature of atmospheric chemistry. It turns out that in areas where you have too much of one of the main ingredients, the NOx, you actually quench some of that ozone chemistry. You will reduce ozone concentrations by increasing emissions of NOx. But when I raise the height of the box, that's effectively diluting the NOx. It's reducing the NOx concentration, and you get more ozone formation in response to that. So in NOx-quenched regions, when you raise the height of the mixing depth, you actually get more ozone formation. And it would be predicted for central Los Angeles, at least, that you would get almost 60 or 70 parts per billion of additional ozone formation in response to that. And so it's important to understand all of those effects because we think that climate change is going to have an impact on all of those variables, temperature, humidity, and mixing depth. We expect all are going to change in response to climate change. What about particles? Particles were the other half of the smog story, right? And so I'm going to look at one size fraction of particles, the PM 2.5 size fraction, all the massive particles smaller than 2.5 microns in diameter. And I'm going to look at the 24-hour average on September 9th, 1993. And so the health-based standard just got lowered to 35 micrograms per cubic meter. And the concentrations during this event were significantly higher than that, 180, 190 micrograms per cubic meter. So again, a severe, severe air quality event. And of course, we compare the model predictions to the measurements. Particle modeling is harder than ozone modeling because ozone is one chemical and particles are 1,000 chemicals. Ozone is a gas phase. Particles are many, many different sizes. And so it's harder to get the particle model to represent reality. But what I'm showing here is observations versus model predictions for two different sites, Azusa and Claremont in Southern California. We've got time on the lower axis again across 2 days now. And the diamonds or the triangles are the observations, and the lines are the model simulations. And although we don't get all the features right, we're definitely getting approximately the right answer for the particle concentrations. And several of the components of the particles, the stuff that makes up the mass, the nitrates, the organic carbon, the elemental carbon, we're getting right. Although every feature of this simulation isn't right, this is about as good as you can do. And we have a feeling then that this will have some accuracy. This model captures at least the main features of the particle formation dynamics, and we think that it will have some skill in predicting what would happen in the future in the presence of climate change. So what would happen if the temperature went up by 5 degrees? How would that 24-hour average concentration have changed? And what I'm showing here is, again, a difference plot. So it's how much more or how much less PM 2.5 would you have on that day if temperature would have got warmer. And instead of seeing increases now, what we're seeing is decreases. You're seeing less airborne particulate matter in response to a warmer temperature. And it's well understood what's driving this. Basically, a big chunk of that airborne particulate matter was ammonium nitrate, a semi-volatile secondary formed contaminant. And ammonium nitrate will evaporate. Hotter temperatures make it evaporate faster. And what this plot basically shows you is a diagram as a function of temperature, how much ammonium nitrate can the gas phase hold before it spills over into the particle phase. And what you can see is that at hotter temperatures, the atmosphere can hold more ammonium nitrate. And so as I increase that temperature, more of that ammonium nitrate that used to be in the particle phase evaporated. So that's one effect that will happen in response to warmer temperatures. It's not to say that the total gas phase nitric acid production is going down. If you look at this upper plot, it actually shows how total nitrate produced changes as a function of temperature. It's just that it's not staying in the particle phase. You start to evaporate it out of the particle phase, and it's going back into the gas phase and then dry depositing to the earth. So we have to think about that change, though, in the context of other things that are going to be happening. Temperature isn't just going to go up, and humidity isn't just going to change. It turns out that background ozone is changing over time as well. Background ozone is the ozone that blows into California from upwind. It's not ozone that we made locally, but we have to deal with it, both in terms of what it does directly to ozone concentrations, but also what it does to the rest of the atmospheric chemistry. Typical background concentrations today are around 30 parts per billion of ozone blowing into California, but that's going up over time. It's going up over time because global emissions of things like methane and NOx are going up as well. And that is driving a general increase in background ozone concentrations to the point where we think in the next 100 years, it's roughly going to double. So instead of 30 parts per billion of background ozone blowing into California, you'll get more like 60 parts per billion. It turns out that additional background ozone has an effect on particle concentrations. And it has an effect on particle concentrations because that ammonium nitrate got made by oxidants in the atmosphere, and ozone can act as an oxidant. And so if you would do a +5 temperature perturbation, but now with 60 parts per billion of background ozone instead of 30 parts per billion, instead of going down uniformly across the whole air basin, some areas are going up, and the areas that are decreasing still in PM2.5 concentrations decrease by less. So you're generally encouraging PM2.5 concentrations with that additional background ozone in the system. This was for the case of constant absolute humidity. If I would do the same thing with constant relative humidity and the additional background ozone, you can see that things are getting even worse, where now some regions are forming even more PM2.5, and the areas that are going down by even less. That's because wetter particles like ammonium nitrate more than drier particles do. And so if you put a little bit more humidity in the atmosphere, the particles are wetter, and you tend to get more ammonium nitrate forming in response to this. So what you'll pick up as I go along is that the ozone question is relatively well understood. There's a lot of weight of science. Everything sort of moves in the same direction. The particle question is a lot more complicated, and you have competing effects. Things are moving in different directions, and it's not clear what's going to be dominant, and that means that we're going to have to do more analysis later on. Same sort of analysis then with the mixing depth, the height of the box that the emissions will mix into. If that went up by 50%, how would particle concentrations change? And you're seeing the same thing that we saw for ozone. Some areas go down just due to simple dilution, and some areas go up because the NOx chemistry basically gets diluted a little bit more. It speeds things up, and you get more secondary formation of pollutants in the areas that were NOx quenched before. Okay, all of that was done for Southern California, Los Angeles. We're worried about Central California as well because there's lots more people that are going to move there in the future. And so we're going to do the same sorts of things. The episode that I'm going to look at for Central California is a winter episode. It happened in January, and that's when we get most of our severe particle episodes in Central California is during the winter. And the temperatures range from almost freezing at night to around a maximum of 15 degrees Celsius during the day. Again, there was a strong temperature inversion, as we have with all of our air pollution events. And then we had light surface wind. These are some predictions of the model predictions versus the measurements for different pollutants. The gas phase pollutants on the left-hand side here, the particle phase pollutants on the right-hand side. This is all for Fresno on January 6, 1996, or January 4th through 6th, 3 days shown on the lower axis here. And all the vertical axes are pollutant concentrations. The pollutant is in the upper left-hand corner. The modeled line is the predicted line is the black line, and the measured line is the blue line. And again, I show this to you to convince you that our model works. We're capturing the major features of the air pollution system. Therefore, you would expect that perturbations are going to have some skill at predicting what would have happened if conditions would have been slightly different. Without this, you wouldn't trust a model result. Never trust a model result unless they show you some sort of data to convince you that it's getting the right answer for approximately the right reason. Okay, so these are the base case ozone and PM2.5 concentrations in Central California. The vertical scale here is ozone in parts per billion. The vertical scale on the right-hand side is for the particles, is particle concentrations PM2.5 in micrograms per cubic meter. Again, I tried to put arrows where the health-based standards are. This wasn't an ozone event. Remember I said I had about 30 parts per billion of ozone blowing into California? You can see the maximum concentrations here are only 30 or 40 parts per billion. Most of that ozone is background ozone that blows into Central California from upwind locations. It's not locally made. The chemistry just isn't fast enough in Central California in the winter. So it's not an ozone episode, but it's still a pretty big particle episode. You've got concentrations of particle, PM2.5, up around 100 micrograms per cubic meter at these urban locations here. The health-based standard, again, is about 35, so 3 times the standard, an unhealthy condition. So how would that change if we had plus 5 degree temperature change and then 60 parts per billion of background ozone instead of 30 parts per billion? And these are difference plots again. So how much additional pollutant do you get? And the ozone responds almost just directly to the background ozone. So I add 30 extra parts per billion, and that's about what I get in the air basin. And that's still not interesting because it's still below the health-based standard. But what you're seeing for the particles is something that is more interesting, where, again, that background ozone is encouraging nitrate formation that contributes to PM 2.5 in some locations, while the temperature is driving it in the opposite direction. So you can see some blue areas here that are decreased PM 2.5 concentrations, where you've got some red areas that are increasing in PM 2.5 concentration due to those competing effects. And so again, it's complicated. Why do we get an increase there and not here? Well, it turns out that most of that increase happens where you've got the highest ammonia concentration. I'll talk a little bit about that later on. So the same thing, only with more water vapor in the atmosphere this time. So this is the difference between the base case and the perturbed case. So it's still got an extra 30 parts per billion, but that's just what I put in on the boundary. That's not interesting. But you're seeing even more particle formation now because wetter particles, again, have a higher affinity for forming ammonium nitrate aerosol. And so you're seeing even more PM 2.5 form in response to that. So why do I have the highest concentrations there? It's actually a pretty complicated plot, so I'm just going to say it in words. It turns out that the particle concentrations are most sensitive to temperature at the location where the concentration of nitric acid and ammonia is almost equal. If you have an area that has a great abundance of ammonia, then it's not as sensitive there. So the temperature effect doesn't shift the PM 2.5 concentrations as strongly where you've got a lot of excess ammonia. So you've got a lot of excess ammonia where you've got a lot of dairy cows, basically. So those regions where the PM 2.5 went up most strongly is the region where you've got all the ammonia emissions, all the dairy cattle are there, and that means that the temperature effect doesn't work very much, and the ozone effect is free to drive things up without very little temperature impact. And so without going into the details of that plot, that's basically how it works. Okay, so and then the effect of mixing depth on the concentrations. Again, ozone is simple and boring in these plots, so I'll focus on particles. How much extra particles would you get if you had a 50% increase in mixing depth? And again, you're seeing regions where you're getting more particle formation, and that's because of that NOx quench chemistry. When you dilute the system so that the NOx concentrations are reduced, then you actually drive the chemistry faster, and that results in more airborne particle concentrations in the system. This is just a summary plot trying to summarize how ozone in the dark bars and PM 2.5 in the open bars will respond to all these different temperature perturbations during 3 different episodes. I talked about the Southern California episode in 1993, and I talked about the San Joaquin Valley episode in 1996. I didn't talk about this one, but it shows the same trend. The circles represent the concentration change where at the location of the peak concentration, and then the bars represent the range of change that happened anywhere within the whole domain. What you can get out of it is basically that and ignore the wind speed ones for right now and focus on the temperature and humidity and mixing depth. Basically, ozone concentrations are uniformly being driven up, but there's competing effects for the particles where these open bars here, you're seeing effects. Some areas are going up, some areas are going down due to these effects happening in different directions. And so we think there's a weight of science evidence for what's going to happen to ozone, but there's still a lot of questions for particles. So we use different techniques to try to get at this question, and I'm going to have to go through this very, very quickly, and I apologize ahead of time, but instead of using our wonderful models, which are lots of fun, and we have really big computers, and it's a great time to drive that, it's loads of fun, we also wanted to use something that was a little bit simpler, to use observations, what's happened in the past, and try to get a feeling for climate sensitivity based on just those observations. And so we call that statistical downscaling, and the hydrologists have been doing this for a while now, where they can predict what's going to happen to stream flow based on some very coarse scale predictions of what climate's going to do. We tried to develop some statistical models to tell us the same sorts of things for what is going to happen to ozone in response to climate change. So the idea is that we'll use historical measurements instead of a model prediction and just try to look at how ozone responds to different climate variables. We looked at a lot of different climate variables, and what we ended up with was using the temperature at around 1.4 kilometers in the atmosphere as the variable that we want to correlate ozone concentrations against. And this is just a shot of what that looks like at Southern California, looking west, so that's downtown Los Angeles, and then looking north where you are in the atmosphere. And there's reasons for why that temperature should affect ozone concentrations. Ozone doesn't get made at the surface. Ozone gets made at the upper atmosphere and then mixes back down to the surface. So the properties in the upper atmosphere matter. And we know that the temperature will affect the rate constants for the speed of reaction. Lots of different things affect that. It's also a marker of how much stagnation you have. And so it works for a number of different reasons. When you first look at the scatter plot of this variable T850 versus the daily ozone concentration, you don't get a lot of insight into what's going on there. There's not really a clear relationship between those two things. But if you go a little deeper and you start looking at probability distributions of ozone as a function of the daily 1 hour max ozone at a given temperature, there's some probability distribution of what ozone concentration you'll get. And we tried to pick apart why this distribution looks like it does. Why is it approximately normal? Why does it have these properties? Why is the spread as much as it is? It would have been nice if there was a really tight relationship where every time you had T850, you got the exact same ozone number, but that's not what happens. You get a whole range of ozone numbers when you look at 30 years of data at any given value of T850. And so we characterized this. Instead of looking at just the mean, we looked at the quartile concentrations. And when you plot the quartile concentrations for ozone concentrations at any given T850, a relationship starts to come out, but you still worry a little bit about why there's so much spread. Why is there the chance that you'll get this ozone concentration or that ozone concentration at a T850 value of 300 or 295 Kelvin? And so we used models to try to perturb the system again to try to figure out what that result should be sensitive to. And we did a lot of different perturbations looking at the effect of temperature, mixing height, relative humidity, overall emissions. So you might have different mixing heights at the same value of T850. You might have different emissions. You might have different, maybe the initial conditions or the boundary conditions were different between those cases. Maybe that explains the scatter. What it came down to is that there's scatter because there's been a long-term change in the emissions inventory for these regions. A or B has been driving for 30 or 40 years to reduce the emissions in Southern California and Central California, and that has had an effect over time. So the value of ozone that you would have got with a T850 at 300 Kelvin 20 years ago is different than the value of ozone that you're going to get today because the emissions inventory has shifted over time. And in words, that explains these pictures where if we use the exact same meteorology, but use a 1987 emissions inventory versus a 1993 emissions inventory, we get very different results. And the bottom line is that the atmosphere has been getting less reactive over time. As you drive things down lower and lower, the temperature sensitivity of the atmosphere has been going down. So ozone doesn't respond as strongly. You can see that this is a tighter distribution with a lower mean value than the 1987 value distribution that we see over here. So with those two things, you can actually see, then once you have that insight, you know what you're looking for, you can actually see this in the data. So if I just plot the ozone concentrations, plot the median value of ozone as a function of T850 for 1980 versus 1989, I get this upper line. 1990 to 1999, I get this middle line. And then 2000 to 2004, I get this lower line. So the emissions over time has been reducing the sensitivity of the atmosphere, and you can see it in the actual measurements. You don't need a model to tell you this once you know what you're looking for. And this is just showing that it actually varies by month as well, but I won't go into that. So once we know that relationship between that T850 value and ozone, we can use that to really efficiently plot long-term trends because you can get T850 directly out of a global climate model without any more modeling that needs to be done. And so this is a plot of what we would predict the ozone concentrations to be, or actually it's the number of days per year that would exceed the 90 part per billion ozone threshold. That where would the day be unhealthy? And what you're looking at is a plot from 2000 to 2100, and there's a general upward trend. And it depends which IPCC emission scenario you use because the ones with less controls of anthropogenic emissions result in more temperature increase, which gives you more days of ozone per year exceeding the unhealthy standard versus the days that try to clamp down on things. So either 0.3 days per year or either 0.7 days per year is the slope of the best fit line. And again, the uncertainty bounds here are just the range between the quartiles, the Q25 and the Q75. But we understand that now. We understand that that is just because of the emissions inventory shifts. And so I'm saying, what if we kept emissions the same? Let's just look at the climate penalty. How would things behave? And so we understand that, Scatter. We don't have to worry about it. The slopes of these lines are significant. So 0.7 days or 0.3 days per year doesn't sound like a lot, but picture it this way. So in 100 years, that means that you would have 30 extra days, one more month per year, where ozone concentrations would be unhealthy breathe in California, all else being equal. That's the climate penalty for ozone. How many more days? That means that we're going to have to clamp down on emissions even more than we would have had to already in order to prevent that from happening. If you have a different global emission scenario, one that's a little less controlling for the climate change gases, then it's 0.7 days, 2 months per year. And it's happening at the tails, the early spring and the late fall. Now you're getting those to be ozone season months as well as the middle of the summer, which we traditionally think is the ozone. Okay, so where do we still need answers? There's a lot of uncertainty in all of this, and it's good to talk about it. One of the main sources of uncertainty is going to be for secondary formation processes. We understand the inorganic salts pretty well, but we don't understand the secondary organic aerosol formation very well. And some estimates already have almost 50 or 75% of the organic carbon in particles in Los Angeles being not primary but secondary. It formed in the gas phase in the atmosphere and then partitioned to the particle phase. We don't understand that process very well. Most air quality models, all air quality models, underpredict that fraction, and that fraction is going to be more and more important in the future because we're going to control the primary particles. We're going to put diesel particle traps on diesel engines. We're going to prevent wood burning. All that primary stuff is going to go away. What's going to be left in the particle phase for organic carbon is going to be secondary in 50 or 100 years from now, and we don't understand how that works, let alone how climate change, how temperature is going to affect that. This is one plot just sort of illustrating that. This is the size distribution of carbon during a recent experiment that we did, and the open bars are carbon that we can explain, and the closed bars are carbon that we can't explain as a function of particle diameter. And this was using tracers, basically, but the air quality models are doing exactly the same thing because the tracers are what we feed into the air quality models. We feed those measured source profiles in. And we can't explain that accumulation mode carbon, and that accumulation mode carbon is going to be more and more important in the future. And we have no idea how that responds to climate change. So that's a real question that we have. So we know some things, and we don't know some things. There's more work to do. And so you have to try to look at, well, what do we have weight of science agreement on between multiple researchers, multiple techniques, versus what are just one or two people saying so far, and then make decisions about where we have weight of science right now, and then keep doing research where we still need answers. So we know that increasing temperature encourages ozone formation. We know there's going to be a climate penalty for ozone. And we know that ozone also responds to other things like humidity and mixing depth. We know that increasing temperature is going to cause some of the particles to evaporate. That's one effect. But we also know that background ozone encourages more formation of particles, and background ozone is going to be going up. So we've got competing effects going in opposite directions for that part of the problem. And so we're going to need additional emissions reductions to compensate for the temperature ozone climate penalty, and we still have more work to do, I think, before we get a weight of science answer for what particles are going to do. We know now more about how the particle system is sensitive to climate change, but because some of the effects act in different directions, then we need more work there. And this is just a quick picture of what we're doing now under sponsorship from ARB as well as from EPA, looking at different aspects of this problem, trying to use more models and more rigorous analysis, taking regional weather forecasting models and downscaling the global climate simulations to the local scale. And then so we know how much temperature change, how much mixing depth change, how much humidity change we're going to get, and we can weigh those things together fairly versus just picking perturbations to look at sensitivity. We can weigh them more fairly and see which effect is going to dominate. And we're also looking at emissions inventories and then feedbacks between air quality and climate. We think that we can see rain shadows between our major cities because of how air pollution affects our weather. And so we're worried about those types of feedbacks as well and whether or not we are capturing those adequately. And so I'm standing up here trying to represent a lot of research that was done by many, many folks, some of them at ARB, some of them at the university. And so I want to acknowledge a few people. First, the funding source. Most of this work has been funded by CARB. And then folks at UCD, grad students currently working on the climate problem. Nezat Motalebi at ARB, who's been very, very helpful through all of this. And then our collaborators down in San Diego, Dan Can and his whole climate team in collaboration. And with that, I'd be happy to try to answer any questions. I wowed you, right? Uh, Background PM is really, really important. We haven't tried it yet, but we know somewhat how it influences the system. So California for years and years has gotten the sulfur out of the fuel, and so we don't make a lot of our own sulfate here. Most of the sulfate aerosol actually blows into California, and so if you measure sulfate aerosol offshore, you see 3 to 5 micrograms of sulfate, and that's what you see inland as well. And so we think that most of the inland signal is actually coming from offshore. So if there's some upwind source that's making that sulfate, and some of it you can argue DMS production in the local surf zone or whatever, but some of it might be long-range transport. And as you know, there's what, a 5 to 7 day transport time, I guess, from China or Asia to North America. You wonder what's going to happen as the energy consumption, the demographics in those areas shift, what we're going to be facing for upwind boundary conditions. So we haven't directly done that, but we have some insights, and you guys know as much as I do or more. So. That's actually in here. And so we have an online UV feedback mechanism for local aerosol formation. We won't get to that in the near term, but for the longer term, as we build our air pollution system into the actual regional forecasting model, instead of doing those two things separately, we'll have that online extinction higher up in the atmosphere. Right now, we've only got that extinction low down in the atmosphere. Natural sources are in that background ozone number, yeah. So they would contribute to that 30 parts per billion that blows in currently, although most of what's going to happen in the future isn't going to be natural. It's going to be driven by anthropogenic. Compared to those other places, yeah. Right. And so you go back to that slide with the London fog event versus the six city study. Yeah. Yeah. I mean, some of those places still have air pollution that is similar to what we had 40, 50 years ago, where you've got really, really severe problems, orders of magnitude worse than what we have here. And so I haven't looked at those places with my models or my techniques, but it goes back to the fact that there's still on the order of 40 or 50,000 people a year in the United States dying from particular air pollution, and maybe 7,000 of those people in California. So it's not to minimize what's happening in other countries, but we still have a problem here, even though we've come a long way through the efforts of ARB in California and through EPA nationally. But we still think that we're having a really serious negative impact. And 40 or 50,000 people, just put it in context, and that's a very round number. So there's big uncertainty. But that's about the same as traffic fatalities in the state. And so those are equally important issues. One of them is harder to see, but equally important. We all know when someone dies from a traffic fatality, but you don't know when somebody dies from air pollution. They had a heart attack, and you can only see with very careful statistical analysis that heart attack was then correlated with air pollution. You don't know when it happened, and it's really hard to pick out individual cases, and therefore it's really hard to make mechanistic links. Traffic fatalities were a lot easier. Okay, they weren't wearing their seatbelt. An accident happened, they weren't wearing their seatbelt. When somebody has a heart attack, you don't know if that's a lifestyle issue or that's an air pollution issue, and it's a very, very complicated process to try to understand mechanistically what drove that. So we only have these statistical estimates right now, but the statistical estimates are scary and it makes the particles smaller. So particles, when they evaporate, get smaller, and to the degree that particle size matters where it deposits in your cardiopulmonary system or your respiratory system, then that would be an important thing to try to consider. We have a lot of other chemical reactions in here trying to predict, okay, if that nitric acid and that ammonia go back in the gas phase, what's it going to do? But both of those things are pretty inert. I know that there's some recent work predicting that you can get NOx back from nitric acid, but we didn't have that in here, and I don't think that's a dominant effect. And ammonia, we think, is pretty inert. So we don't think that that's going to turn around and contribute to something else. The answer is different if you look in the East Coast versus the West Coast, I think. Some of those nonlinear effects, when you take the sulfur out of fuel and you make less sulfate, but then the available stuff makes more nitrate. And so there are some nonlinearities, but not in this one particular issue that we're looking at. So AB32 deals with greenhouse issues, which are somewhat related but somewhat different from anthropogenic pollution. And so I haven't looked at the actual impact of AB32 on urban air quality, but I know from talking to folks that and just how California works, there's a commitment to meet the health-based standards in California, and so we're definitely going to get there. It's just a question of how much climate penalty will we pay along the way. And so if climate change makes it harder for us to get there, we're going to spend another $1 billion or whatever we're going to spend in order to get there, but we're still going to get there. So I think what I'm trying to do is quantify the magnitude of that climate penalty. Questions back? Yeah, so global dimming is one of the questions that came up. So in the air quality models right now that we don't have feedback to local meteorology. That's a couple of years away for us still under sponsorship from EPA. But that eventually will go in there. We don't think that that's a dominant effect for local global cooling. Although maybe other folks who have looked at that know more about it than I do. We do know that the pollution shades part of the solar spectrum that drives the chemistry, and so the part of the solar spectrum that drives the chemistry is actually the really shortwave stuff in the blue, so blue that you can't see it range, and that stuff, the particles definitely interfere with that, and so we've got those feedback effects in there right now, but we don't have the feedback effects in actual temperature change. One more question if somebody wants to take one last shot. Thank you. We'll make a final one now. Thank you for the old fashioned. Yeah, the old school.
I thought that was great. But just the right level.
Yeah, I tried to have something for everybody.
Yeah, you can see those folks in there.
Oh yeah, I mean, some of these guys know more about some of these people. Hi, Joe. How are you? Hi. How are you doing? Yeah. I hope it was entertaining. Yeah. Anytime you want to talk, let me know. Send me an email if you want to chat about climate change and air quality. I seem to be more and more focused on it. Right. As we all are. Yeah, nice to see you.
My name is Adwela. I work here.
The name is
Ajit Adwela.
Ajit runs the modeling group for planning and technical support. So when we talk about modeling all these episodes,